All right, thanks everyone for being here. I'm very excited to be here and to be giving this presentation, especially this early in the morning. And before we get started, I wanna, oops, that was too fast. I want to start with the credits because it's not just me. This is an entire project with many people contributing to this, and this is also the only way this is possible because we need to do a lot of work and write a lot of drivers. I unfortunately don't have time to call out all of these amazing people who help us support and all of this, but I want to specifically mention Marken, who originally started this project years ago, built much of the tooling and many drivers and supported a lot of the other contributors. And without him, none of this would have been possible. So I'm very happy that, that he started this. And he's probably one of the biggest contributors to this project. We also have Alyssa, who led the graphics driver work and built a fully conformant user space stack for this completely unknown GPU. We have Asailina, who wrote the GPU kernel driver. There's Janne, who's doing downstream kernel maintenance. There's people working on audio and all kinds of other stuff. So without all of these amazing people, this would not be possible, and I'm very glad that I'm working with these. And I forgot a few of them here, but thanks to everyone who made this possible, and also thanks to all these people who contribute donations, which allow us to buy hardware and fund development. And finally, thanks to the people who actually helped me build the slides in the past days. Now that being out of the way, let's get started with the talk. I will roughly have three sections. At first, I'll talk about the past a little bit, how the project was started, and how all this tooling we have is built, and how we actually reverse engineer hardware. Then in the next section, I'm going to show how I used this tooling to reverse engineer the Type-C ports and build USB support and so on. And then at the end, we have a brief outlook about the M3, M4, M5 chips, which are currently not supported in our project. Just to give you a state and what our plans are there. So let's get started with the first one. Apple, as many of you may probably know, announced that they are going to move to ARMX with their own silicon back in 2020. And Marken, a few days later, announced that he would love to port Linux to these and started a Patreon project so that he could work full-time on this, and reached enough funding pretty quickly, and then announced that he would do Asahi Linux in December 2020. Mainly due to his work, in a few months later, he already managed to get the first patches into the upstream kernel tree, which allowed the thing to boot to a very, very simple shell. But this was already the first amazing step because it required a lot of customizations and patching a few things around because these things are different quite a few ways from regular machines. And then about a year later, in early 22, we released the first alpha of Asahi Linux for end users so that they could install them on their machines and actually put a proper operating system onto this amazing hardware. The one question that we always get is, how is this even possible? Because if you're familiar with most of Apple's devices, these are fairly locked down. So you can't just put Android onto your iPhones or to your iPads because Apple controls the entire boot chain. They want all code to be signed, and they just don't allow you to put any custom code on there. And people assume that this must be the same for Macs, but that's actually not true. On these Macs, they just allow you to boot any code you want. So Mako is the binary format that Apple uses on their architecture. And they put significant effort into engineering a system that you run your own custom code on these without compromising the security of Apple's code. So what you have to do, you have to boot into what Apple calls one true recovery, which has two conditions. The first one, you have to be physically in front of the machine. So you have to long press the power button, do a full hard reboot, and there's some early stage code that way makes sure that you're sitting in front of the machine, that it is not some malicious code running on your machine, but that you actually intentionally move to this recovery thing. And then you have to authenticate with a machine owner password. Machine owner is usually the very first account created originally. And only then you can just run a command. It's going to be a bit scary because it's going to say, this is going to drop security, blah, 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 and so on. But then you can just run your own completely unsigned code, and this is intentional. And with that code, you get dropped into EL2, so that's exception level 2 for those of you who are not familiar with ARM architecture. And this is the highest privilege level on the CPU. And there's no management engine on top. There's no firmware running on top on the CPU. There's no more Apple code running on the CPU. It is running on coprocessors, but we don't care about that. But on the main core, you get full control. And like I said, this took some significant engineering effort from them. This is not just an accident. So they really made this possible. And they made this possible. They just want to stress again, there's no exploits or similar required. This is intentionally done by Apple. So we are not even hacking anything here. and not even voiding the warranty. And that is the guy who built this from Apple. He's no longer at Apple now. And he tweeted a while ago that he specifically designed this mechanism to allow any code the user wants to boot. And the way this works is you just create a secondary partition. So in the beginning, the CPU will start from some secure ROM, which can never be changed. It's going to load a bootloader called iBoot. This is all Apple code from a NOR flash. And that bootloader, you then have a boot menu where you can select what you want to boot. And if you want to go to macOS on the left side, it's going to run with fully security intact. There's no way to compromise this, but you can also just go, oh no, I want to boot this other weird thing here. And you get a copy of a secondary partition and can run your custom boot object there. They have a nice boot picker, and you can put your own picture there. So what we did is we just put our own pictures that when you click on there, it's going to boot to Linux. The one issue is, of course, that there's no documentation. So we just get dropped to this CPU. It's a single core is running, and we have no idea how any of the hardware works. And to get started to port Linux, the first things you need is an interrupt controller and a timer. Without these Linux just cannot work. But once you have these two, you can essentially already drop to a very, very simple Linux kernel. The timer is just the normal ARM one, so nothing needed to change there. But the interrupt controller is already the first custom device that Apple built, and this is called the Apple Interrupt Controller, or AIC for short. There's no documentation. Apple will never provide documentation, of course. There's also no driver available. But we know where this lives in memory. And we also know how these registers from this controller are called from OpenSURE drops. And so what Marken did back then, because he knows how interrupt controllers work, he just tried to, or his approach was to figure out, if I just poke these registers, can I figure out how this hardware actually works, and then build a Linux driver. But one problem is that if you just start by this and running your own code, you always have to go back to one-to recovery, do a full boot cycle, and usually the first iterations just don't work all that well, so you're going to spend a lot of time rebooting, installing another boot object, and so on. This is very annoying. So instead, he focused on building reverse engineering tools that makes this life much, much easier. And we've all met back then from console hacking, and back on the Wii was the first time we used this. We built something called Mini, which is a small C application, standalone a freestanding C application that provides a small proxy over UART. And on Apple Silicon, you can find this UART over some of the USB pins. So you have a hardware UART, and then this way you get a Python shell on a separate machine, which allows you to poke and play with hardware registers. So if you want to try out anything, you don't have to write new C code, reboot again, and whatever. You just have a second machine, have a Python shell there, and you just play with the hardware. And it's going to send this over to UART to the other one, execute it, and return back the results. And this makes reverse engineering so much easier, because you can, for example, write something that reboots your machine. So if you messed the hardware up in some way and you need a full reset, just run Python reboot on your main machine. That's going to reboot your target. You can also use a shell.py, which drops to a small Python shell, and then you can send read or write commands over the UART to the Apple Silicon device and figure out how the hardware works. You can also allocate memory there if you need a memory buffer and put stuff there. You can monitor MMIO ranges. There's a lot of work went into just making the reverse engineering as awesome as possible and as quickly as possible. And you can prototype drivers and have a very, very quick development cycle. And this is really important if you're reverse engineering unknown hardware, because you will need a lot of trial and error to figure out how this works. And you don't want to do this inside the Linux kernel, which is also a very complex piece of software. You want to do this as easy as possible, as quickly as possible, so that you first know how the hardware works and how to drive it, and only then go ahead and write the Linux driver. And just an example how this works. So this is so back then I wrote an I2C driver, and I wrote the first prototype inside Python. And what you can really do is you set some registers at the beginning, then write some registers, and then pull some other register until the transaction is done, and then write the results back in there. And this is all, before I even touched a single line of Linux kernel code, it's really writing Python on a host machine and seeing how this reacts and getting this to work there. And once it works, then you at least have a hardware model in your head, and then you can write the driver, and at that point, you know that all the bugs are probably in your driver code and not in your understanding of the hardware. And this makes for a really amazing development experience. And this blindly poking registers, it works quite well for the simple hardware, like for the I2C bus, because there's only so many ways you can build an I2C controller. So you can fairly easily just guess how it works if you find register names or something. But these machines also have much, much more complicated hardware, like the GPU, for example, or some of the coprocessors, where you have no chance in hell by just guessing to figure out how this works. Now, what you could do is you could load XNU into a disassembler and CERN to disassembly, but I've done that enough in my life. I don't want to do that anymore. It's also fairly annoying code because it's written in C++ and IOKit, and usually the drivers are spread across multiple kernel extensions. So it's just not fun to reverse engineer all of this, and we'd much rather observe how this drives the hardware. And what we can do, or what Markin then built, was build a way to observe how XNU drives the hardware. And so MMIO on top is memory mapped I/O. That's how you talk to the hardware. EL2 is the highest exception level running on ARM machines. And usually XNU runs in there. And then down you have user space, which we don't care about much at this point. And what we want to figure out is how does XNU talk to this MMIO interface. And what he did was to push XNU one level below, run it inside a VM essentially, a very custom-built VM, and make Mini act as a or M1N1 act as a hypervisor. And we originally just map all the hardware through, but then we can say, okay, this one piece of hardware we're interested in, we can change the page tables in such a way that every register access results in a trap. So when XNU tries to access the hardware, it goes to Mini. Mini then logs that register access and sends it over USB to another computer. And that's the setup we then have. Then is again a device under test where we have all this running. Then a host machine where we get essentially a trace of what the hardware is doing. And this can also all be configured because a lot of tooling was built around this. And one example you can do, if you have figured out some registers, you just define these in Python. So this is for the USB 2 file. You just, because XNU is very, very verbose in its debug output, and if you correlate the debug output with the register writes, you can then just write down, yeah, this is how the register looks like. You can build a tracer and just start this tracer on the host machine. And then it's going to pretty print all the access that XNU does for you. And this way you can iteratively construct your understanding of how this hardware works. So at the beginning, it's just raw MMIO writes. But then you get an understanding of what some of these registers do. You give them names, and then you see in your log, you see how these registers slowly take shape, and you slowly build an understanding of how all this hardware works. And this works really nice for very complex hardware. And if you have put your effort into building all this tooling, this is what you then see on your host machine. For example, in this case, you can see some system register access from XNU. You can see some MMIO access. This is in the Power Manager region, how it changes some registers. We can also emulate hardware, of course. For example, if you want some hardware, we don't want XNU to touch in certain ways because we maybe have messed with it a little bit. We can emulate this. For example, the starting CPUs, we just emulate inside the VM. Or we can just print all the accesses we see on that other machine. And this usually allows to reverse engineer much of how this works without even opening it as assembler. Now, sometimes you need to because sometimes you can't tell from where this is going. But I'd say that for most of the hardware, this is much, much quicker, because it kind of feels like if you're a software guy, there's stuff like strace, and this kind of feels like you're building strace for hardware. And this makes for a really nice developer and reverse engineering experience. And now with all this, so you reverse engineer all the hardware, and the result of all this is essentially you pipe curl to bash, wait 10 minutes, follow the instructions, and then you get a fully working Linux distribution with graphic acceleration and lots of hardware support on your machine. Now, and this was, like I mentioned earlier, in the beginning, there was a lot of feature work. So we built a lot of features, but we didn't upstream these originally. So we had like over 1,000 downstream pages in our fork of Linux. And that's just not a great situation to be in. It's great if you want to build features quickly, but it's not so great if you actually want this to be sustainable. Because in the end, we don't want to build distributions for Apple Silicon. We just want all distributions to just work. And the only way to make that work is to upstream these patches into the Linux kernel. And that's when earlier this year, some of you familiar with the project might have known that a bunch of people stepped down because they didn't want to work on this anymore. You can read all about it online, I'm not going to go into that. But we also used that to change the approach and say, OK, now we're going to fix our technical debt, essentially. We're going to clean up all these drivers and get them upstream before we focus on new features. And so this year was a lot of upstreaming about the system controller, USB 3, some audio stuff, not all of it, parts of the GPU, especially the user space. And we're in much better shape now. We still have two fairly big kernel drivers, the display controller and the GPU, that are only downstream. but we will continue to work on pushing these upstream. And yeah, that's our current focus, just upstreaming all these things before we build new features. And now that I've talked about how the reverse engineering tooling and all that works, I'm going to walk through how I used all of this to reverse engineer the USB ports and what makes them so special and why they are so complicated, why it's so complicated to support them on these machines. Now, USB is fairly old. In 1996, the first version dropped 1.5 Mbits. They called it low speed. 2 years later, they realized this is actually quite nice of a bus, so we could need more bandwidth. Let's do full speed. Well, eventually this was also too slow, and after full obviously comes high speed with USB 2. So this is 480 Mbits per second. Again, today this is still slow, so we're going to do super speed with 5 gigabit per second. Because this naming was not confusing enough, we're going to do super speed plus with 10 gigabits per second. Now at this point, even the USB implementers forum realized that maybe the naming gets a little bit of confusing, because if you tell a random person, oh yeah, I have a USB full speed device, you would expect it's very fast. Well, it's actually very, very slow. And so what they finally did was that when they introduced the 20 gigabit version, they just called it USB 20 gigabit per second. And they changed all the names. I mean, not all of them, they kept low, full, and high, but all the others, they just changed the marketing names to essentially just how fast the USB actually is to make this a bit easier. And then in 2019, we got USB 4, which does up to 40 gigabit per second. And USB 4 is a little bit special because it's not just another iteration of USB with more speed. This is actually Thunderbolt, open source version, because the specification is fully available. It's very, very long. And USB 4 then also supports stuff like PCIe tunneling and DisplayPort tunneling and so on. But the point I'm trying to make here is that this is a very complex piece of hardware with lots of moving parts that we all have to get supported. And while improving the bandwidth, they also need new connectors at some point. So originally, you're probably all are familiar with USB A and B, and there's mini and micro, and then the USB 3 variants, and so on. So there are lots of these connectors. You probably know how it goes. You always need 3 tries to get these things working. And at least in theory, with USB-C, this is no longer the case. So this is the new connector, which has a lot of pins. It's symmetric, so at least in theory, you can just rotate it, and everything will work fine. And this can also carry a lot of different signals. And all the modern Macs just have many of these ports, essentially. And finally, you can at least, that's the goal, everything is correct. One caveat, because people implement this wrong, you can, even with USB-C, you can make it such that it only works in one orientation. They have a bunch of cursed devices that only work in a single orientation or cables. So unfortunately, this does not work out, but otherwise, this is a fairly amazing connector. And like I mentioned, it supports, on these machines, 4 different protocols. There's the very low speed USB 1 and 2. There's USB 3. Then you have Thunderbolt or USB 4. And final DisplayPort. And we have to get all of these things supported. And the way this is usually implemented in hardware, this is the very rough overview diagram. You have USB 2, which still to this day uses separate lanes. So you still have the D plus and D minus. It's almost differential signaling. And even if you buy a modern USB 4 or Thunderbolt 4 dock, you will still have these D plus and D minus lanes, and that dock will contain a USB 2 hub, because this protocol cannot be tunneled over all of the rest. The rest all happens over these high-speed lanes. In USB, it's SS, TX, and RX for super speed transmit and receive. And there's a bunch of differential pairs in this controller. But because you have different protocols, you need to negotiate, because both ends need to speak the same language. And so you need some way to figure out which protocol do we want to speak. And that happens over the line that's called CC and a USB power delivery controller. And this controller, when you plug it in, it's going to negotiate and figure out which mode both ends support, and then decide what the hardware is going to do. And then there's a switch that switches these high-speed lanes to one of the 3 different hardware components. But this also means that to get this working, there's at least 5 or 6 moving parts in here that all have to work together. And on Apple hardware, none of these are documented, obviously. And this was the situation when I started. But with the reverse engineering tools we have built, I'm going to now walk you through how you can approach this and this really big problem and tackle it step by step and make these things work. So from the iPhone hacking scene, because these machines are essentially at the beginning very big iPhones, because they built these chips, Apple Silicon, over the past 15 years or so, and at some point realized, oh wow, these chips are so fast, we can actually build desktop machines with that now. And we know from the iPhone hackers that Apple used to use this Synopsys Designware controller version 2. So maybe they're still using it on these machines. And what I figured out pretty quickly by just dumping the MMIO from my computer and comparing it with known USB controllers, it's almost the same. It's the version 3 of this controller. And as it goes, you can't find an official datasheet for this unless you're a big company and willing to sign NDAs and so on. But all the registers, if you just Google for one of these register names, you find datasheets by Intel or Rockchip who have built SOCs and just include all the documentation in there. So I'm not sure why the official one is ND8, because you can find anything in the open anyway, but usually that's how it goes. So the first step is always use Google, try to find, even if the official datasheet is under an NDA and you can't find it anywhere, maybe it's just in some other SOC documentation where you get enough information of how to implement these things. There's also a Linux driver for this, which is very nice. And it even used to be dual licensed, BSD and GPL many years ago. So even if you're building a more permissively licensed software, you can still use this as a reference. They just switched, I think it was in 2016. You just have to go back to the old commits and make sure you don't use any of the newer code. So this is awesome. This is essentially documented. We just have to implement this. And back then, to use a Mini and all this reverse engineering, you had to build a hardware serial. And that was fairly annoying because you have to speak USB PD, you have to build a 1.2 volt level shifter and all that. And so the first thing I did was just implement a USB gadget mode. So CDC ACM is just the USB class that does serial, and implemented it in M1N1. It seemed to only work once. So when I disconnected the plug and plugged it in again, it just never showed up a new connection event. I just thought, OK, I just messed up. It's probably a dumb bug somewhere. This works fine for now. Let's instantiate this in Linux and see what happens. It also only works once. So if you connect it, the first time you see the connect event and everything goes on, but the second time it just doesn't show up and you don't see this. So this seems weird. And the other part is that this only works in device mode. So I could emulate a serial device or a USB storage on the Apple Silicon machine, but I could not plug in a USB stick or any device that you would actually want to use. And my suspicion was, because I then checked that those devices just don't get power, because we never touched the power controller at this point. And Type-C can carry a lot of power these days, up to 240 watts. So I was told a few days ago that there's only one device that actually uses this full power. But apparently you can carry quite a bit of energy over these lanes. And so you need negotiation, because otherwise you're just going to burn down all your hardware. If like an unexpected small phone suddenly gets 240 watts pumped into it, that's not going to go well. So this is why there's always power negotiation going on, and why the default mode is don't apply any power at all. That's this protocol over the CC lens that I mentioned a little bit earlier. And like I also mentioned, this also does alternate mode negotiation. And on Apple Silicon machines, this is handled by a TI-based USB PD controller. It's not called TI anymore, but there were some references in the code, in the strings, where you could see, OK, this is probably an old TI chip. On the left side, you can see what I did there, because there was some details there to figure out from the firmware. So I got one of these from, I think it was AliExpress, and debugged it, connected JTAG, and dumped the whole firmware of it to figure out some details. But this was just at the very end. The more important part is there was a Linux driver. And we just had to change, by tracing it all again, we just had to change a few things and actually make this work. And then, yay, USB host mode works. But it still only works once. So you get to use your Linux device or your USB device exactly once, which is not really what you want to do, because these days you plug in USB devices a lot, so it's time to figure out why this is going wrong. And this is, again, a situation where this reverse engineering tooling that was built is so amazing, because if you wouldn't be able to do dynamic tracing, you would now have to go and figure out, OK, why does this only show up once? And you could go down into so many rabbit holes, because USB 3 is such a, or even USB 2 is such a complicated thing to drive. And you could go into, there could be so many things going wrong, and you probably would take a long time to figure out why you never see a second plug event. But if you have built all this tracing and identified many of these registers, you just boot into XNU, plug a USB device, unplug it again, plug it again, and then take a look at the log you got over USB to figure out what's going on. And in this case, what I found very suspicious was that suddenly, after I plugged it out, like a few milliseconds later, it asserted a full reset of the USB controller. Then it asserted a reset of the port and the bus. And then it gated clocks and everything. So it turned the whole system completely off. And then when I plugged it in again, it did the whole thing in reverse. So it turns out that their controller is so messed up that if it's been initialized once, it can never be initialized again. So you have to, every time you disconnect the USB device and connect it again, you really have to tear down this entire thing, assert the hard reset line, and then bring it back up again. So like I said, you get the interrupt from the PD chip with a hot plug. You then only power it up and bring everything up. Hopefully USB device works, usually does. Then you do the unplug the interrupt, and then you have to tear everything down and do a hard reset again. Now, and this is to be implemented inside Linux, which I tried, and my original implementation was pretty hacky because I used the USB role switch code to hack this in there, and we kept that for over a year because I thought, oh yeah, this is quite ugly, I'm not sure how to do this correctly, and so on. And this is one of the things where I can only encourage you, if you're working on Linux, try to do upstream as early as possible. Because when I sent around these series, like 2 days later, the maintainer of the driver mentioned, oh yeah, this is probably not a nice way to do it, but I have a much better way. How about you do it like this? I was like, oh wow, I should have done this from the beginning. So upstreaming not only helps you maintain your code, it also makes your code better, because there are people out there who really understand the driver and know precisely, if you tell them what you need to change for your hardware, they can essentially tell you, oh yeah, this is the best way to do this. And so again, upstreaming, good idea. Do this as often as possible. And with that, we have USB 1 and 2 fully working. And now I could show the same slide for USB 3 and so on, but it's really the same process. So USB 3 is a bit more complicated because it's much, much higher speed, and USB 2 is fairly tolerant of the hardware you put in there. With USB 3, you have to link training and make sure that the bits you send on the one end arrive the same on the other, and so on. There's clock recovery and all this kind of weird hardware magic. And so what you do is just the same thing. You just observe the MMIO again, see what it's doing, try this with a few different devices, and then just write a PHY driver. And this was finally upstreamed a few days ago. So now we also have USB 3 support in the upstream kernel. Next one is the DisplayPort. And DisplayPort, people really want this. So this morning, I randomly just looked for, when I was finishing the slides, I just looked for people asking for DisplayPort. Of course, there's someone, it works like a charm, it's everything great, but my external screen doesn't work. Then you look into our subreddit, you always find on the first page someone wondering, why does DisplayPort not work, and so on. And essentially because it's complicated. There's a separate display controller that you have to set up and speak a very weird serialization protocol, actually 2 or 3 of these, because 1 is not enough. And you have to build this all together with the USB 3 PHY that was upstreamed. And then you can maybe get DisplayPort working. But for those people who are in the audience here, you can probably see I'm giving this from an Apple Silicon machine. And this is running Linux, just as a proof. So we finally have this working now, and I was very nervous if this actually worked out today. And this was really mostly Janne spending the last days, and he gave me kernels, and we tested it and so on. And now it seems to be in a state where it's mostly working. Let me see if it's full screen again. And we pushed the code that enables this probably a few minutes ago. Right now it's meant for developers to help us iron out the last bugs. So if you want to contribute, this is one example. You could take a look at this tree, compile your kernel, see if it works with your screens, and if not, see if you can debug this and figure out why it isn't working. And our goal is to make this generally available for all people sometime early in the next year, once we've done a few more developer testings and so on. But if you're a developer, feel free to check this out, and feel free to help us bring Linux to these awesome machines. And yeah, with that, we have DisplayPort. And speaking of contributing, I promised that at the last part of the presentation, I was going to talk about the future of M3, M4, and M5. And like I mentioned earlier, we are all pretty much focused on upstreaming and not on new features, which is the right move in our opinion, but we were hoping for new people to help us, especially with M3, M4, M5. We'll get to them eventually, but new contributors are always nice. And one of the things is that so many drivers are already built that the differences between something like M1 and M2 and M3, they are generally minor. Because Apple also has no incentive to change their hardware much. Because it costs them money, they have to write all their drivers again, then they have new bugs again, have to fix them again. So they really have no incentive to change a lot on most of these machines. I mean, they might do minor changes, like moving one chip from one bus to another because they found a new source for the chip, or because they want to reduce BOM costs, or because maybe just the routing of the PCB is better. But these are very, very minor changes. Or maybe in some NVMe, they change how some register works, or how the interrupt controller works, how co-processor communication changes. But these are all things that if you're an experienced systems engineer, and you can probably figure these out. So it still takes some time and some experience, but this is not really rocket science because we have all these amazing reverse engineering tools. The one exception is the GPU, because there still innovation happens, because AI and all that and whatever they need, they're still building innovation. And especially on M3, this is going to need significant work to get this working. But the good news is that, so these were just our assumptions. And we were hoping someone would step up, and the good news, just that happened. So we had a new contributor, Integral Pilot, who has been working on M3 bring-up in the past weeks. And yesterday, he shared some screenshots and some progress. And it boots on his, I think it was the M3 Max now, with all the cores. It boots, the storage works. He fixed all the minor issues that were around. There's no graphics acceleration yet, which, as I said, will take a longer time. But you can, of course, already play Doom. And again, we're going to continue working on this. This is still in the very, very early stages, but hopefully next year we will going to continue to make progress there. Then I have a few more minutes left, not a lot, but I will very briefly talk about M4 and M5. In general, it's the same story. So probably minor changes again here and there. Not a big deal, but there is one unfortunate change that happened, which makes this a little bit more annoying. In the beginning, I told you that we have XNU and EL2, like the highest level, and use it to trace the MMIO. But this was kind of a lie. It's a bit more complicated because Apple likes to extend the ARM architecture, so the ARM architecture to their liking. And what they did in this case introduced something they call guarded levels, which use the same page tables as the normal level, but they modify the permission bits in the page table. And they do this because XNU is a fairly large attack surface, and they don't want you to be able to already own their whole system if you just find any bug in any random kernel driver. So one of the things they did, they introduced originally the iPhones this page protection layer, which runs in a higher privilege level, and only that one is allowed to modify page tables. And this is all fine. We reverse engineered all of this, and we're virtualizing all of this on M1 and M2, and M3 as well. But with M4 and M5, they disable these instructions for us. We don't know why. Maybe it is because ARM doesn't like them doing this, or doesn't like them allowing everyone to play with these instructions, because they like to keep the instruction set very, very straight and contained. But that's just our best guess. But still, we now get on M4 and M5 two boot modes. One of them, if you want to boot XNU, you get dropped into EL2, but Apple code is already running. And it's running in GL2, and you can't port Linux to this mode. But Apple still added another mode, because like I said, this has all been intentional. They want people to be able to run their own code with what they call raw boot objects. And there you get dropped into the same mode that you always have been. So you can port Linux just fine to this. There is no roadblock. It's just, someone just needs to do the work. The only problem is that this breaks our reverse engineering tools, because we now can't virtualize XNU anymore. We can't do the hardware as tracing anymore. So this makes reverse engineering much, much, much more annoying. But if anyone wants to step up and help us with these problems, I've already talked to a few people in the past few days. I'm going to skip over the solution because I don't have that much time anymore. But feel free to reach out to me. I'll be at the Fail Overflow assembly for another hour or two or so before I leave. You can also send me a mail, follow me on Fedi wherever I go to our website, see what's installed, or just come to IRC if you want to contribute in any way. And other than that, thank you very much for your attention. We hopefully have time. Yeah, we still have a bit time for a Q&A now. Thank you.
Yes, it's only a little time. So if you want to have, if you have a question, stand up, go to the mic, and we try to do this really quick. And we start immediately with microphone number 1.
Hi, thanks a lot. I love my SI, and I will love it even more after DisplayPort is working. Thanks for the great work. The quick question, what's your thoughts on why Apple really allows to run other code on their hardware? It doesn't seem there's any incentive for them.
I mean, I can just guess. My best guess is that they're selling a computer, and with a computer, people expect to be able to run their own operating systems. With an iPad or an iPhone, people just don't expect that anymore. So that's my best guess, but I have absolutely no idea.
Microphone number 2.
Thank you for the talk. I have a question on your slide about the USB and DisplayPort support. You conveniently skipped over USB 4 or Thunderbolt support. What's the state of that?
The state of that is that's what I'm going to work on next. So DisplayPort is mostly Janne at this point, and I'm going to start working on USB 4 and Thunderbolt now. We roughly know how it works. And there's also a nice driver in the kernel from Intel that does most of the work we need. We need to adjust that a little bit. The thing that's going to be tricky is PCI hot plug, because at least when I was trying, especially if you plug very complicated Thunderbolt chains like a dock after a screen after a dock or whatever, the hot plug code is not very happy with that. So we'll have to do some work there probably. But we have a rough idea how it's going to work, and hopefully sometime in the next year, but I'm not going to promise any timelines.
Thank you.
Last question from microphone number 4.
Hi. Thanks very much for the work and the talk. I've got a question about bus topology with USB, because you mentioned that if you essentially plug and unplug devices, you need to restart the controllers. How does this affect all other USB devices on that bus?
So you only have to tear down the entire controller if you unplug something at the root ports of the MacBook, and each of the ports has their own USB controller. So you only have to reset that one port, and all the rest is going to be totally fine and not break. And so this just works out.
Thanks.
So really last question, because there's still people lining up. Sven, it's for me. Sven, when people still have questions, where can they find you during the last day of Congress?
Yes, so I'll be hanging out at the Fail Overflow Assembly in, I think it's hall 3 or 4. So you can find it on the navigation, and I'll be there until probably around 2 or so today. So just come by, stop by, say hi. I'm happy to answer all your questions there. Otherwise, just reach out to me on some other way.
Thank you very much. And this is your applause.
Thank you very much.
Thank you very much.